A pleasant day, everyone. We are the Good Five, and today we will going to report an interesting topic entitled Our Star, the Sun. But first, allow me to share to you the learning goals of our topic for today. To life on Earth, the sun is the most important object in the sky. It lights the days, warms the planet, and provides the energy for life. But to astronomers, the sun is simply a typical main sequence star, located conveniently nearby for detailed study. In this chapter, we take a closer look at the Earth star. By the conclusion of this chapter, you should be able to first describe the balance between the forces that determine the structure of the sun. Second, explain how mass is efficiently converted into energy in the sun's core. Third, sketch a physical model of the sun's interior and describe how observations of solar neutrinos and seismic vibrations on the surface of the sun test astronomers' models of the sun. Fourth, describe how energy is transported through the sun. Fifth, describe the solar activity cycles of 11 and 22 years and explain how these cycles are related to the sun's changing magnetic field. And lastly, explain how solar activity affects Earth. We are expected to meet these goals at the end of the lesson, so please lend us your ears in order for you to understand our report. Now, I would like to share first what really a sun is. By human standards, the sun is eternal. It rises in the east every morning, sets in the west every evening, and shines brightly as it crosses the sky. Like all the stars, though, the sun undergoes constant change. Some of the changes take place over days or even minutes. Others require decades, and still others require millions or billions of years. The sun was born about 4.6 billion years ago from the gravitational collapse of a vast cloud of gas and dust. Material in the center of the cloud was squeezed so tightly that it became hot enough to ignite nuclear fusion. Today, the sun continues to fuse hydrogen atoms to make helium in its core. It fuses about 600 million tons of hydrogen every second, yielding 596 million tons of helium. The remaining 4 million tons of hydrogen are converted to energy, which makes the sun shine. Most of this energy is in the form of gamma rays and X-rays. Now, let us deepen our knowledge about the sun that will be given by other members. Mr. Martinez, take it away.
Good day, everyone. My name is Francis L. Martinez, and today I will discuss to all of you about the structure of the sun. The sun may be average as far as stars go, but that makes it no less impressive as an object on a human scale. The mass of the sun is 1.99 times 10 raised to the power of 30 kilograms. It is over 300,000 times than the Earth. The sun's radius is 696,000 kilometers, and it is over 100 times than the Earth. And the sun's luminosity is 3.85 times 10 raised to the power of 26 watts. The sun can be divided into six layers or regions. The innermost layer of the sun is called core, where nuclear fusion occurs. Then, the next layer is the radiation zone, and the next layer is the convection zone, and the next layer is the photosphere, the lower atmosphere in what we see. And the next layer is the chromosphere, the orange-red layer of atmosphere, thousands of miles thick. And the last layer is the corona, the uppermost part of the atmosphere, millions of miles thick. The sun's atom counts are 91% hydrogen and 8.9% helium and 0.1% heavier elements such as carbon and nitrogen. The first key balance within the sun is the balance between pressure and gravity. The sun is a huge ball of hot gas. If gravity were stronger than pressure within the sun would collapse. Conversely, if pressure was stronger than gravity, the sun would blow itself apart. The balance between the two is called hydrostatic equilibrium. Hydrostatic equilibrium establishes the pressures at each point within a planet and determines the atmospheric pressure at Earth's surface. The blue arrows that you can see at the figure that goes outward represent the push of pressure, balanced with the blue arrows that goes inward that represent the pull of gravity, and the red arrows that you can see in the figure are the energy rejected from the surface of the sun balances the energy produced in its interior. And that's all about my topic, and let's proceed to the next reporter.
Next topic, the sun is powered by nuclear fusion. The nuclear fusion is the process where the two light nuclei were combined together, releasing an energy. Nuclear fusion is a very efficient source of energy where the lighter nuclei fuse together to form heavier nuclei and release of energy in the process. Deuterium and tritium undergo nuclear fusion releasing energy. Mass can be converted to energy and energy can be converted to mass. And the quantity of energy released follows Einstein formula, which is E is equal to mc squared, where E is the energy, m is the mass, and c is the speed of light. We can calculate the energy released by this mass to energy conversion. Hydrogen is the most abundant element in the universe. The fusion of hydrogen nuclei is the source of the sun's energy, where the fusion of four hydrogen nuclei converted into single helium in the core of the sun, and this process is often called hydrogen burning. According to theoretical studies, the sun's energy comes from the nuclear reaction and it is produced in its innermost region, which is the core. Also, the sun releases energy at produces the equivalent of 38,460 septillion watts, or 3.85 times 10 to the power of 26 watt per second. Nuclear reactions converting hydrogen to helium are the source of sun's energy. In these reactions, in the core of a low-mass star such as the sun, hydrogen burns primarily through a process called the proton-proton change. The image shows the three steps of proton-proton change. Step 1, colliding two protons together to make deuterium. One of the protons is transformed into a neutron by emitting a positron that is like an electron but with a positive electric charge, and neutrino, a hard to detect particle. Step 2, a proton crashes or collides into deuterium nucleus, making helium-3. Energy is released and carried away as a gamma ray that has a very high energy photon. Lastly, collide two helium-3 nuclei together, releasing a helium-4 and ejecting two protons in the process. The second image shows electric repulsion. In order for atomic nuclei to fuse, they must be brought close enough to each other for the strong nuclear force to assert itself. And all atomic nuclei have positive electric charge, which is protons, so any two nuclei repel each other. In letter A, when two atom nuclei are moving slowly toward each other, what happens is they are being pushed apart by an electric repulsion. While in letter B, the atomic nuclei are moving faster towards each other and they can only get closer. And in letter C, under these conditions, atomic nuclei slam into each other hard enough to overcome the electric repulsion at a high temperature and densities. Then fusion takes place and released energy. Radiative transfer, it carries energy from hotter region to cooler regions by photons, which carry along the energy. Although radiation flows in both directions, more radiation flows from the hotter region to cooler region than from the cool to hot regions. Therefore, radiation carries energy outward from the inner parts of the sun. The sun is divided into zones based on where energy is produced and how it is transported outwards. That there are three zones: the core, the radiative zone, and the convective zone. The core is at the center, its hottest region, where the nuclear fusion reaction that power the suns occur. Moving outward, next comes the radiative zone. Its name is derived from the energy it carried outward through this layer, carried by photons as thermal radiation. The third region of the solar interior is the convective zone. It is the dominant mode of energy flow in this layer. Heat moves upward via rolling convection, then energy from the sun's surface.
Good morning, everyone. I am Racyl S, and I was tasked to discuss about the interior of the sun. We all know sun is the source of an enormous amount of energy which provides Earth with light and heat necessary to support life, right? And the core of the sun is buried beneath 700,000 kilometers of dense hot matter. Based on studies, sun is however much hotter at 15 million degrees Celsius or 27 million degrees Fahrenheit. So imagine how hot the core of the sun is. Sun is transparent to neutrinos because neutrinos are the product of nuclear fusion. Like for example, our sun is constantly doing nuclear fusion, which is the conversion of the hydrogen to helium to produce heat and light, which will come here on Earth. Astronomers use neutrinos to observe the heart of the sun. Neutrinos are the most abundant particles in the universe because neutrinos are so common with their mass, which remains unknown and is thought to have an effect of the gravity of the Earth. Even we are just lying in our bed at night, about 400 trillion solar neutrinos pass through our body each second. It is also produced in nuclear fusion processes that power the sun and stars. Yes, because neutrinos are born due to the process of nuclear fusion in the sun. And take note that there are three types of neutrinos, or the flavors of neutrinos, and these are the electron neutrino, muon neutrino, and tau neutrino. The neutrino was long thought to have zero mass like photons and to travel at speed of light. But if neutrinos actually do have a tiny amount of mass, then theorists from the particles physics predict that solar neutrinos should oscillate, means alternate back and forth among three different kinds or flavors. So here, as seen in the figure 14, letter B, electron neutrinos should also change flavor as they interact with solar material during their escape from the sun. And neutrino also travels very nearly at the speed of light. Yes, since they have mass, there is no such reason that they couldn't travel at any speed. So these are the neutrinos telescope or neutrinos observatory used to observe neutrinos produced in the heart of the sun. Actually, scientists started looking for those electron neutrinos in the 1960s, but only one-third to one-half of the predicted number of neutrinos showed up in the detectors, and this became as the solar neutrino problem. And because of that, it starts with the first neutrino telescope, as we can see here in the first image, which is the homestake neutrino. This was actually the experiment led by Ray David Jr. They used 100,000 gallons tank of dry cleaning fluid to search the neutrino and was housed a mile underground in the caverns of the Homestake gold mine in South Dakota. We have also here in the second image, we have the SNO Plus Sudbury Neutrino Observatory. This was built as a water Cherenkov detector dedicated to investigate elementary particles called neutrinos. And the last image, we have the artist's conception of the Antares Neutrino Observatory, which is able to detect all neutrino flavors. So these are among the neutrino telescope enabling astronomers to directly observe the results of nuclear reactions going on there. Aside from those telescopes, heliosseismology can be also used to probe the sun's interior. So heliosseismology is the study of wave propagation in the sun. It is also confirmed the predictions of solar models. Yes, this technique actually provides a powerful test of an understanding of the solar interior. Let's say geologists use the seismic wave from the earthquakes to probe the interior of the Earth, whereas solar physicists use the surface oscillations of the sun to test their understanding of the solar. And yes, we called it heliosseismology. In short, if there is earthquake, they measure the waves. The same thing happened in the sun. There are also waves from within that they measured. With this, it can tell us information about the surface of the sun and gives us clues to the composition of the interior of the sun as well.
So we are already done tackling the interior of the sun. Now let's move on to the atmosphere of the sun. An overview of the sun's atmosphere on that figure shows that it is made of several layers that lie above the top of the convective zone. The sun's atmosphere is where all visible solar phenomena takes place. At the base of the atmosphere is the photosphere, the sun's apparent surface. This is where features such as sunspots can be seen. Above this photosphere is the chromosphere, a region of strong emission lines. The top layer is the corona, which can be viewed during the solar eclipse as the halo
around the sun. Solar prominence is caused by the sun's magnetic field poke out into the corona. In the sun's atmosphere, the density of the gas drops very rapidly with increasing altitude. Based on the figure, it shows how pressure and temperature change across the atmosphere of the sun. In this section, we will explore each of these layers beginning at the bottom with the photosphere. Next slides, as we all notice in that figure, the sun appears to be fainter near its edge than near its center. This effect called limb darkening due to the structure of the sun's photosphere. Near the edge of the sun, you are looking through the photosphere at a stepped angle. As a result, you do not see as deeply into the interior of the sun as when you are looking directly down through the photosphere near the center of the sun's disk. The light you see coming from near the limb of the sun comes from a layer in the sun that is shallower and hence cooler and dimmer. Next slide, the sun's outer atmosphere, chromosphere, and corona. So based on the figure, the image of the sun showing fine structure in chromosphere extending outward from the photosphere. The chromosphere is seen during a total eclipse. This eclipse images shows the sun corona consisting of million Kelvin gas that extends for millions of kilometers beyond the surface of the sun. Next slides, we have the solar activity caused by magnetic effects. The sun's magnetic field causes virtually all of the structure seen in the sun's atmosphere. High resolution of images the sun show coronal loops that makes the sun looks as it through it were covered with matte tangled hair. So as we have noticed in that figure, it's just like a tangled hair. It is fibrous or rope-like textures in the chromosphere is a result of magnetic structure called flux tube. Now in the second figure, the magnetic field in the solar wind gets wound up by the sun's rotation. Consequently, the solar wind has spiral structure resembling the stream of water from rotating lawn sprinkler. The effect of the solar wind are felt throughout the solar system. The solar wind causes the tails of comets, shapes the magnetospheres of the planets, and provides the energetic particles that power Earth's spectacular auroral displays. Next slides, we have the figure of sunspots. A large sunspot is pictured on the two figures. The remarkable structure of one of these blemishes on the sun's surface of the sun. Each sunspot consists of inner dark core called umbra, which is surrounded by less dark region called the penumbra. The penumbra has an enteric radial pattern reminiscent of the petals of the flower. Observation of the sunspot shows that magnetic field that resemble the shape of the horseshoe. The number of the distributions of the sunspots change over time in the pronounced 11-year pattern called the sunspot cycle. At the beginning of the cycle, sunspots begin to appear at the solar latitudes of about 30 degrees to the north and south of the solar equator. During the following years, the regions where most new sunspots are seen move toward the equator as the number of sunspots increases and then declines.
Good day, everyone. I am the last reporter, and I will be discussing the topic was given to me, which is the origin, the solar wind, and life. Solar flares and coronal mass ejections can affect the space around Earth. In fact, energetic particles accelerated in solar flares pose one of the greatest dangers to human exploration of space, and they need to be considered when astronauts are orbiting Earth in a space station or someday traveling to the moon or farther. Earth's magnetic field protects life on the surface from these energetic particles. Thanks to this magnetic field, the particles travel along the magnetic field line to the poles, creating the auroras without bombarding the surface and causing danger to life on Earth. But the moon does not have this protection because its magnetic field are very weak. Astronauts on its surfaces would be exposed just as astronauts traveling the space would be. The strength of the solar wind varies with the solar cycle, as noted in section 14.4 exposure dangerous varies as well. The sun sends out a constant flow of charged particles called the solar wind, which ultimately travels past all the planets to some 3 times the distance to Pluto before being blended by the interstellar medium. This forms a giant bubble around the sun and its planets, known as the heliosphere, in what we see in the figure. And actually, NASA studies the heliosphere to better understand the fundamental physics of the space surrounding us, which in turn provide information regarding space throughout the rest of the universe. as well as regarding what makes planets habitable. The solar wind is a gas of charged particles known as plasma, a state of matter governed by its own set physical laws, just as the more common solids, liquid, and gases are. As the solar wind sweeps out into space, it creates a space environment filled with radiation as well as magnetic fields that chill all the way back to the sun. This space environment is augmented by interstellar cosmic rays and occasional concentrated clouds of solar materia that burst off the sun, known as coronal mass ejections. This complex environment surrounds the planets and ultimately has a crucial effect on the formation, evolution, and destiny of planetary system. For one thing, our heliosphere acts as a giant shield protecting the planets from galactic cosmic radiation. Earth is additionally shielded by its own magnetic field, the magnetosphere, which protects us not only from our solar and cosmic particle radiation, but also from erosion of the atmosphere by the solar wind. Planets without shielding magnetic fields, such as Mars and Venus, are exposed to such processes and evolve differently. In addition, NASA studies of the heliosphere include research into how the solar wind behaves near Earth, what causes instantaneous magnetic and electric fields around other planets, how does heliosphere interact with the stellar medium, what the boundaries of heliosphere look like, what is the origin and evolution of solar winds and interstellar cosmic rays, and what contributes to the habitability of exoplanets. The field is, therefore, intensely cross-disciplinary. Heliospheric research often works hand in hand with planetary scientists, astrophysicists, astrobiologists, and space weather researchers.
That is all for today. These are all of our references. We hope you learn from us. Thank you and God bless us all. We are the Group 5.